Medium wave is the part of the medium-frequency radio band used mainly for AM radio broadcasting. For Europe, the MW band ranges from 526.5 kHz to 1606.5 kHz, and in North America an extended MW broadcast band goes from 535 kHz to 1705 kHz. Propagation characteristics: wavelengths in this band are long enough that radio waves are not blocked by buildings and hills and can propagate beyond the horizon following the curvature of the Earth. This is called the ground wave. Practical ground wave reception typically extends to 200 to 300 miles, with longer distances over terrain with higher ground conductivity, and greatest distances over salt water. Most broadcast stations use ground wave to cover their listening area. Medium waves can also reflect off charged particle layers in the ionosphere and return to Earth at much greater distances. This is called the skywave. At night, especially in winter months and at times of low solar activity, the ionospheric D layer virtually disappears. When this happens, MF radio waves can easily be received many hundreds or even thousands of miles away, as the signal will be reflected by the higher F layer. This can allow very long-distance broadcasting, but can also interfere with distant local stations. Due to the limited number of available channels in the MW broadcast band, the same frequencies are reallocated to different broadcasting stations several hundred miles apart. On nights of good skywave propagation, the skywave signals of distant station may interfere with the signals of local stations on the same frequency. In North America, the North American Radio Broadcasting Agreement sets aside certain channels for nighttime use over extended service areas via skywave by a few specially licensed AM broadcasting stations. These channels are called clear channels, and they are required to broadcast at higher powers of 10 to 50 a kilowatt. Use in the Americas. Initially, broadcasting in the United States was restricted to two wavelengths. Entertainment was broadcast at 360 meters, with stations required to switch to 485 meters when broadcasting weather forecasts, crop price reports and other government reports. This arrangement had numerous practical difficulties. Early transmitters were technically crude and virtually impossible to set accurately on their intended frequency, and if two stations in the same part of the country broadcast simultaneously, the resultant interference meant that usually neither could be heard clearly. The Commerce Department rarely intervened in such cases but left it up to stations to enter into voluntary time-sharing agreements amongst themselves. The addition of a third entertainment wavelength, 400 meters, did little to solve this overcrowding. In 1923, the Commerce Department realized that as more and more stations were applying for commercial licenses, it was not practical to have every station broadcast on the same three wavelengths. On May 15, 1923, Commerce Secretary Herbert Hoover announced a new band plan which set aside 81 frequencies, in 10 kHz steps, from 550 kHz to 1350 kHz. Each station would be assigned one frequency, no longer having to broadcast weather and government reports on a different frequency than entertainment. Class A and B stations were segregated into sub-bands. Nowadays in most of the Americas, medium-wave broadcast stations are separated by 10 kHz and have two side bands of up to a plus or minus 5 kHz in theory, although in practice stations transmit audio of up to 10 kHz. In the rest of the world, the separation is 9 kHz, with side bands of a plus or minus 4.5 kHz. Both provide adequate audio quality for voice, but are insufficient for high-fidelity broadcasting, which is common on the VHF-FM bands. In the US and Canada, the maximum transmitter power is restricted to 50 kilowatts, while in Europe there are medium-wave stations with transmitter power up to 2 megawatts daytime. Most United States AM radio stations are required by the Federal Communications Commission to shut down, reduce power or employ a directional antenna array at night in order to avoid interference with each other due to nighttime-only long-distance skywave propagation. Those stations which shut down completely at night are often known as daytimers. Similar regulations are in force for Canadian stations, administered by Industry Canada. However, no daytimers exist anymore in Canada, the last one having signed off in 2013 after migrating to the FM band. Use in Europe. In Europe, each country is allocated a number of frequencies on which high power can be used. The maximum power is also subject to international agreement by the International Telecommunication Union (ITU). In most cases there are two power limits, a lower one for omnidirectional and a higher one for directional radiation with minima in certain directions. The power limit can also be depending on daytime, and it is possible that a station may not work at nighttime, because it would then produce too much interference. Other countries may only operate low-powered transmitters on the same frequency, again subject to agreement. For example, Russia operates a high-powered transmitter, located in its Kaliningrad exclave and used for external broadcasting, on 1386 kHz. The same frequency is also used by low-powered local radio stations in the United Kingdom, which has approximately 250 medium-wave transmitters of 1 kW and over. Other parts of the United Kingdom can still receive the Russian broadcast. International medium-wave broadcasting in Europe has decreased markedly with the end of the Cold War and the increased availability of satellite and Internet TV and radio, although the cross-border reception of neighboring countries' broadcasts by expatriates and other interested listeners still takes place. Due to the high demand for frequencies in Europe, many countries operate single-frequency networks. In Britain, BBC Radio 5 live broadcasts from various transmitters on either 693 or 909 kHz. These transmitters are carefully synchronized to minimize interference from more distant transmitters on the same frequency. Overcrowding on the medium-wave band is a serious problem in parts of Europe, contributing to the early adoption of VHF-FM broadcasting by many stations. However, in recent years several European countries have started moving away from medium wave altogether, with most all services moving exclusively to other bands. Stereo and digital transmissions. Stereo transmission is possible and offered by some stations in the US, Canada, Mexico, the Dominican Republic, Paraguay, Australia, the Philippines, Japan, South Korea, South Africa, and France. However, there are multiple standards for AM stereo, with CQUAM being the most common in the United States as well as other countries, and receivers that implement the technologies are relatively rare. In September 2002, the United States Federal Communications Commission approved the proprietary Ubiquity in-band on-channel HD radio system of digital audio broadcasting, which is meant to improve the audio quality of signals. The Digital Radio Mondiale IBOC system has been approved by the ITU for use outside North America and U.S. territories. Antennas. For broadcasting, mast radiators are the most common type of antenna used, consisting of a steel lattice guide mast in which the mast structure itself is used as the antenna. Stations broadcasting with low power can use masts with heights of a quarter wavelength to 5/8 wavelength, while high-power stations mostly use half wavelength to 5/9 wavelength. The usage of masts taller than 5/9 wavelength with high power gives a poor vertical radiation pattern, and 195 electrical degrees is generally considered ideal in these cases. Usually mast antennas are series excited. The feed line is attached to the mast at the base, so the base of the antenna is at high electrical potential and must be supported on a ceramic insulator to insulate it from the ground. Shunt-excited masts, in which the base of the mast is at a node of the standing wave at ground potential and so does not need to be insulated from the ground, have fallen into disuse, except in cases of exceptionally high power, 1 MW or more, where series excitement might be impractical. If grounded masts or towers are required, then cage aerials or long-wire aerials are used. Another possibility consists of feeding the mast or the tower by cables running from the tuning unit to the guys or crossbars in a certain height. Directional aerials consist of multiple masts, which need not to be from the same height. It is also possible to realize directional aerials for medium wave with cage aerials where some parts of the cage are fed with a certain phase difference. For medium wave broadcasting, quarter wave masts are between 153 feet and 463 feet high, depending on the frequency. Because such tall masts can be costly and uneconomic, other types of antennas are often used, which employ capacitive top loading to achieve equivalent signal strength with vertical masts shorter than a quarter wavelength. A top hat of radial wires is occasionally added to the top of mast radiators, to allow the mast to be made shorter. For local broadcast stations and amateur stations of under 5 kW, T&L antennas are often used, which consist of one or more horizontal wires suspended between two masts, attached to a vertical radiator wire. A popular choice for lower-powered stations is the umbrella antenna, which needs only one mast 1/10 wavelength or less in height. This antenna uses a single mast insulated from ground and fed at the lower end against ground. At the top of the mast, radial top-load wires are connected which slope downwards at an angle of 40 to 45 degrees as far as about 1/3 of the total height, where they are terminated in insulators and thence outwards to ground anchors. Thus the umbrella antenna uses the guy wires as the top-load part of the antenna. In all these antennas the smaller radiation resistance of the short radiator is increased by the capacitance added by the wires attached to the top of the antenna. In some rare cases dipole antennas are used, which are slung between two masts or towers. Such antennas are intended to radiate a skywave. The medium-wave transmitter at Berlin Bridge for transmitting RIA is used to cross dipole mounted on 530.5-meter-high guide masts to transmit the skywave to the ionosphere at nighttime. Receiving antennas. Because at these frequencies atmospheric noise is far above the receiver signal-to-noise ratio, inefficient antennas much smaller than a wavelength can be used for receiving. For reception at frequencies below 1.6 MHz, which includes long and medium waves, loop antennas are popular because of their ability to reject locally generated noise. By far the most common antenna for broadcast reception is the ferrite rod antenna, also known as a loop stick antenna. The high permeability ferrite core allows it to be compact enough to be enclosed inside the radio's case and still have adequate sensitivity. See also, medium frequency band, of which the medium wave band forms a part. AM radio, long wave, MWDX, shortwave, FM radio, satellite radio, list of European medium wave transmitters, Wave Plan of Geneva, references. External links, building the broadcast band, the development of the 520 to 1700 kHz MW band, M3 map of effective ground conductivity in the USA. MWLIST Worldwide Database of MW and LW Stations, www.mcircle.org. The Medium Wave Circle. A UK-based club for medium wave DXers and enthusiasts. 1. List of long and medium wave transmitters with Google Map links to transmission sites.